This video is part of the MCAT chemistry video course. Subscribe if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll cover VSEPR theory, which goes over electron geometry and then molecular geometry. Before going over this video, make sure you're good on what electron groups are, which that was covered in the hybridization video. So electron groups are, remember, the lone pairs and atoms around a central atom. And what VSEPR theory says is that the electron groups, so those atoms and lone pairs, will repel each other and then space out as far as possible. And we do have lone pairs and bonded atoms, and lone pairs will actually repel the other groups more than bonded atoms will. But as far as the MCAT is concerned, that effect is pretty minimal. I can't think of any instances where it's actually been the deciding factor in a question, so I really wouldn't worry about the tiny differences in angles that you're going to see as we go through this. And then that repelling effect gives a 3D shape to the electron groups around that central atom, and that is called the electron geometry. And we're going to look at that electron geometry for all of our different hybridization and electron groups as we go through this table right now. Here's a table and some images that show us how our electron groups determine our hybridization, and then that also is what determines our electron geometry. So all sp2 molecules are going to have a linear electron geometry, and then so on if you look at the chart and see how those hybridizations correlate with the electron geometries. And if you're not familiar with hybridizations, then I would just go back to that video and watch that and see how those correlate with the number of electron groups. Starting with number one here, sp hybridization. When we have two electron groups, we have a linear electron geometry. So all you're doing is looking at the X bonded to those two Y's and seeing that that molecule would have a linear structure because those two Y's are going to repel each other as far as possible, which is going to give you a bond angle of 180 degrees between those two Y's. And that would be the same even if you took one of those Y's and replaced it with a lone pair. It doesn't matter if it's a lone pair or a bonded atom. We're still just counting the angle between the electron groups. Next, we have three electron groups, which is sp2 hybridization. So number 2 down here for our images. And if you look at these bonds, they would have 120 degrees between each of them. And then that would result in this triangle-shaped molecule. And all of those atoms are in the same plane as the page. So that's a flat shape that you're looking at. And we describe that as trigonal planar. Our next one with 4 electron groups is sp3 hybridized. So number 3 in our images here. And here is when we introduce this concept of dashes and wedges. And a dash, so this Y here, that's pointing into the page. And then the wedge is pointing out of the page. So the wedge is coming towards you. The dash is going away from you. So this molecule has a 3D structure to it. And if you were to measure the angles between these electron groups, you would get 109.5 between any two that you decided to measure the angle between. And I really wouldn't worry too much about where we get those angles from. Just kind of accept that when they space out as far as possible, these are the angles that result. And this shape is described as tetrahedral. And again, this one becomes a 3D shape. So the other two shapes were all in the plane of the page, but now we're dealing with 3D shapes. The next one has 5 electron groups. So number 4 down here. And we never covered this in hybridization whenever we have 5 electron groups. It's just not super high yield enough. The questions that are most likely to come up with 5 electron groups are about geometry, so it's kind of more worth talking about now. But just kind of accept that whenever you have more than 4 electron groups, one of the d orbitals hybridizes with the sp3, so there's just an extra orbital coming from that d subshell. And this shape gives us 2 bond angles, and the 2 bond angles, the first one is 120, and that happens between our 3 underlined Y's right here. So what you basically have is like a trigonal planar molecule, but there are 2 additional Y's, the circle ones, that are bonded to that trigonal planar molecule. So the 120 degrees is between all of the underlined Y's. And then the 90 degrees are between the circled Y's and one of the underlined Y's. So if I made a right angle shape between one of those circled Y's and then one of the underlined Y's, that is where we get that 90 degree angle. And that's for any one of the circled Y's and the underlined Y's. You could choose whichever ones you want and draw that 90 degree angle shape. So if you try to imagine what this shape is, we have that trigonal planar shape in the middle of it, and then we have a Y, and then we have a point that goes above it and a point that goes below it. So you end up with this shape that looks like two triangle-based pyramids that are positioned base to base. And they give us this name, trigonal bipyramidal, which pretty much just describes just that. Our last one is with 6 electron groups. So now we take 2 d orbitals from the d subshell, so it's sp3d2. The angle between all of these would be 90 degrees. So if we were to try and imagine this as a 3D shape, the angles between any one of those would be 90 degrees. So if we want to say we have underlined y's again and circled y's, the angle between 2 adjacent underlined y's would be 90 degrees. And then also the angle between a circled y and one of the underlined y's, that would also be 90 degrees. And this would just give you an 8-sided shape, which is called octahedral. Before we move on to molecular geometry, just have to heavily emphasize that any one of these bonded elements that are represented by Y could be replaced by a lone pair, and your electron geometry is unchanged. You treat it the exact same, and you would just treat that lone pair like it's a bonded atom, pretty much. Now we'll look at molecular geometries, and this is when you do not count the lone pairs. So for all of these geometries, we're only looking at the shape that forms by looking at the bonded atoms. So you'll notice that in this chart, when you have no lone pairs, all of the geometries are the exact same as the electron geometries because the shape ends up being the same if you don't have any lone pairs. Because then you're just counting all of the electron groups, which is exactly what we did for the electron geometry. So first, let's just look at when we have 2 electron groups, which we already know is sp hybridized. So we're looking at our sp hybridized one. When there are no lone pairs, we end up linear, just like the electron geometry. The next one is sp2, which corresponds to 3 electron groups. And then when there's no lone pairs, it's trigonal planar. When there's one lone pair, remember we're only counting the bonded atoms. So then that shape becomes something that's called bent. Next, for sp3, or 4 electron groups, no lone pairs, tetrahedral. And then when there is one lone pair, we end up with this funky shape here. And remember that the dashed y is pointing into the page. So if you try to visualize this, again, we're only counting the bonded atoms. And this is a 3D shape. You end up with basically a pyramid with a triangle base. So we get this name, trigonal pyramidal. Now, if there are 2 lone pairs, we have a non-3D molecule, which is just another bent shape. Now, something you want to make sure you're aware of is that if we go back to the electron geometry and we remember our angles, the first bent that we saw with the sp2 hybridization, that angle was 120 degrees, but the angle for the bent over here is about 109.5 degrees. And technically the angles that we just wrote are actually, they should be a little bit smaller than what we wrote because those lone pairs are repelling those bonded atoms a little bit stronger. But I would not really worry about that. So now we'll look at the molecular geometries whenever we have 5 and 6 electron groups. Before we go over these, I just want to say again that I would definitely not worry about these near as much as the other ones that we just went over. When you have 5 and 6 electron groups, that's just going to be a lower yield topic than when you have between 2 and 4 electron groups. And I'd also recommend pausing the video right now, go back to electron geometry, look at the angles that we talked about for the sp3d and sp3d2 molecules, and then see if you can figure out what all of these angles are between these bonded atoms. First one we'll look at is sp3d. So when you have 5 electron groups, and then again with no lone pairs, it's just the same as the electron geometry. If we have one lone pair, that's going to happen to one of these horizontal y's. One of those will become the lone pair. And then if you try to visualize this in the 3D way, and then turn this molecule on its side, then it kind of looks like a seesaw, and that's where we get the seesaw name. And your angles here would be 120 between those y's there, and then the 90-degree angle between the circled y's and an underlined y. So the circled y, underlined y's, 90 degrees between them. The degrees between the 2 underlined y's would be 120. Next, with 2 lone pairs, we have this T shape. And so 2 of our underlined y's from the original picture there on the far left have become lone pairs. And then all of the y's here are in the plane of the paper. So this just looks like a T, and then all of your bonds would be 90 degrees. Finally, with 3 lone pairs, the 3 underlined y's became lone pairs, and then your angle is just 180 degrees between that top and bottom bonded atom. Now moving on to sp3d2, with no lone pairs, we are octahedral. When you add 1 lone pair, you end up with what looks like just a pyramid with a square base, so that's where we get the square pyramidal. And then the degrees is 90 degrees between any of your atoms on this that you decide to measure. So whether it's between the y's that are underlined or with the circled y, all of those degrees would be 90. Next, with two lone pairs, that ends up giving you a molecule that's basically just a flat square. So that's where we get the square planar molecule. And then again, you have 90-degree bonds, 90-degree angles between all of your bonds. With three lone pairs, we end up with another T-shaped molecule, and again, 90-degree angles between your bonds. Lastly, with four lone pairs, that will end up being linear, which will create a 180-degree bond angle between those two bonded atoms.